Okay, I was asked to do a homework problem before we get started, so let's look at this, the last homework problem on the homework assignment that should have been due tonight, as opposed to the one that's due tonight that should have been due on Wednesday. And the problem says argon gas has several industrial uses. Why would argon gas have several industrial uses? What's special about it? Okay, it's a noble gas. It's also a heavier noble gas, right? Helium, neon, argon. It's heavier than the common ones. When you buy like double pane or triple pane windows, typically they fill them with nitrogen. But if you have them filled with like argon, they actually will have better thermal properties, or krypton even better. Okay, and those are just a couple things. So they sell them in cylinders, kept at a pressure of, and mine it's 216 PSI. What's wrong with, okay, I'm going to highlight it. What's wrong with this statement right here? That's not room temperature. What is room temperature? 20 degrees Celsius, which is 68 degrees Fahrenheit. So that number is randomized, so everybody, of course, has to do their own problem instead of, hey, I worked it out, the answer was 7. Okay, great. Okay, moving on. In this problem, you may assume that the ideal gas law still holds. Remember, to be an ideal gas, you have to have it is diffuse gas. And if you're holding it at 216 psi, that's what, 15 atmospheres? It's probably not something we'd consider diffuse at this point. So that's why it makes that statement, so you still use the ideal gas law. So how much average kinetic energy in joules does each atom of the argon gas in the cylinder have? A numeric value is expected, not an expression. So we're going to find the number, not just the equation. So how do we relate temperature to average kinetic energy? It's this pretty simple equation. If it's a monatomic ideal gas, which argon is, then the average kinetic energy is 3/2 kT. So doing that calculation, AVG, 3/2 kT equals 3/2 1.38 times 10 to the minus 23 joules per Kelvin is K, and then the temperature. So what is the temperature? Okay, I'll do it the way that Max said. It has to be in kelvins. If it's not a change in temperature, it's got to be in kelvins. So then you just pop that in the calculator, and out comes your answer. This thing in parentheses is units of kelvins, so the kelvins are going to cancel with these kelvins, and you're left with joules for your units. Part B, if the volume of this cylinder is 195 liters, how many moles of argon inside? Now we have to use, well, what do we have to use? We have to use the ideal gas law. PV equals nRT. It asks us how many moles, so that's why I have the form with nR, because I'm looking for n, the number of moles, not capital N, the number of molecules. So if you just solve that for n, and so our pressure is 216 psi. Our volume is 195 liters. Our temperature is, I'm going to add those together. So 291.15 kelvins is our temperature. And then R. Okay, so Aaliyah quotes me a number. What's that number, Aaliyah? 8.3 and 4. What are those units?
Joules per mole.
Now, if we look at this, we have two issues. What are the two issues? PSI and liters. We have to be very careful with our units. This is a correct equation. I don't have to cross it out or anything. I didn't make a mistake. But if I just punch in this number, it's not going to be the right answer because it'll have wonky units. So what's the standard unit for pressure? Pascals, actually. So I'm going to multiply this by pascals on top and PSI on bottom. And 1 atmosphere is 101325 pascals. 1 atmosphere is to 3 significant digits, 14.7 PSI. You should, no, you don't have to have these memorized, no. And you should look that number up to have more than 3 significant digits in the conversion factor as well. So don't just use these conversion factors and then say, I did exactly what he did and I still got it wrong. Because I know that 14.7 is an approximation. And then we have liters on top, so I need liters on bottom. And what's our standard unit for volume? Meters cubed, because standard for distance is meters, standard for volume is meters cubed. And so now I need the conversion factor there. And what do I know? I know that 1 centimeter cubed is equal to 1 milliliter, which means 1,000 centimeters cubed is equal to 1 liter. And then I have to say, how much is 1,000 centimeters cubed? Right? My life's not getting easier because I'm trying to do things by memory instead of looking up the number, which is what you would probably do. So I'll take this and multiply by. No, I'm almost there now. 1 meter per 100 centimeters and cube that because it was centimeters cubed. So this is 10 to the minus 6 times 10 to the third meters cubed equals 1 liter. So that's 10 to the minus third meters cubed. That's the correct number, right? And so then if I put all of that in my calculator and multiply it through, then I'll have the number of moles present. So using the part A, the result from the kinetic theory of gases calculation. Part B, the ideal gas law. What was difficult was just the unit conversion. Any questions? Okay, then let us start with the, oh boy, I thought I had this open. Give me just a second to open the presentation because apparently I did not. I was actually in here really early today, which is probably why it's not. Okay, first thing, remember that survey that I asked you to fill out last week? Only one person has filled it out. So please go to Moodle. If we go to Moodle here, the place to find the survey is right there where it says course survey under assignments in the top section. So right above the actual assignments is where the course survey is. So please do remember to do this, right? I can't really take your feedback to improve the course if you don't give me feedback. Okay, back to the presentation, which now is up and running. In class on Wednesday, oh, come on, really? Okay, in class on Wednesday, it's just going super slow. We talked about the kinetic theory of gases. So the problem we just did is an example of using kinetic theory of gas. Today, we're going to be talking about the mechanisms of heat, something I've been intending to talk about for a week, and the greenhouse effect. There was not a perusal assignment for today. I postponed it because I've fallen behind. There will only be one of the two that are currently set for Monday. It'll be the first of the two. I'll postpone the other one and figure out how to do this eventually. So let us get into this. First, talk about evaporation just a little. Evaporation, we talked at the very beginning of the segment on fluids about the different states of matter, the solid, the liquid, and the gas. And a liquid, the molecules can move past each other freely, but they can't escape from each other. There's a certain energy necessary to escape, what we call, conveniently enough, the surface energy or the surface tension. It's two different words for the same thing. So when you have molecules moving around in the liquid, if they get to the surface and they're moving fast enough, they have enough kinetic energy to break free. But if they're not moving fast enough, they don't have enough kinetic energy to break free, and they basically rebound back into the fluid. So first thing to note is, which molecules are allowed to escape? The ones that are moving faster or slower? Faster. In terms of temperature, are those the hotter molecules or the cooler molecules? The hotter ones. So when you have evaporation, only the hottest molecules escape. The coolest ones remain. So what's going to happen to the average kinetic energy if you lose your highest kinetic energy molecules? It's going to decrease, which means that the temperature decreases. So evaporation causes a decrease in temperature because the hottest molecules escape. It's not like you have some crazy energy problem. The hottest ones escape, the cooler ones remain. Now, if I have a vessel that's open to the atmosphere, I have water molecules in the atmosphere, molecules that have escaped from water. And when those water molecules hit the water, they go into the water. And so you're going to have molecules escaping, molecules entering. If I put a lid over it, the molecules that escape stay right there in my vessel. And so they're going to come back, and I'm quickly going to reach an equilibrium so that I have the same number of molecules leaving per second as I have coming in per second if it's a closed vessel. And in that case, we say that there's a number of ways of talking about this. The vapor pressure above there is equal to, the partial pressure of water in the atmosphere is equal to the vapor pressure of water. We can say that the humidity is 100% relative humidity. Notice the word relative. Relative humidity is a measurement of and once again, there's multiple ways of saying this, but it's a measurement of how much water is in the air divided by how much water the air could hold. So if the air can't hold much water, you can have 100% humidity without much water in the air. If the air can hold a lot of water, you have a lot of water in the air for 100% humidity. But what it means is you have that ratio, 100% humidity, the amount of water in the air is what it can hold. So in the picture to the right, where it's reached equilibrium, what's the humidity inside of that vessel? It's going to be 100%. The one on the left is probably going to be less than 100%. And if it's less than 100%, that means you're going to have more molecules leaving than coming in. And so what's going to happen to the water level in vessel A over time? It's going to decrease. What's going to happen to the water level in vessel B over time? Stays the same. So we live in Nebraska. If you put a cup of water on the table today, and you look at measure the height, and you come back tomorrow and measure the height, what are you going to find?
It should increase.
It should drop. if you did the same experiment in August, what would you find? What's that? Probably. Well, in August, the relative humidity here will be relatively high. And if the relative humidity is relatively high, that means you have close to the same amount coming in as you have going out. And so if you do that in July, it's hardly going to drop at all. In fact, we went to Colorado for a couple months, and we left water in a cup, and we came back, and there was still water in the cup after a couple months because the humidity was relatively high. So why does evaporation cause cooling? The molecules with the highest temperature are the ones that are allowed to leave. So if I have water on my skin, that water is going to have some molecules that leave, and then the water's temperature drops. What happens to my skin? It cools. What does it mean for my skin to cool? That's right. It's not that the temperature drops, it's that it loses heat, because my body's going to try to keep the temperature of my skin constant. But it loses heat, and I feel that. It feels cold because of the heat going out of it. So that's why you have, on a hot day, you spray water on yourself and you'll feel cool. Depending on where you are. If it's here in Nebraska, it doesn't cool you as much. If you do the same thing out there in Colorado where I live, it'll cool you a lot because it's very low humidity all year round. Anybody heard of a swamp cooler? Okay, we have some people know what a swamp cooler is. A swamp cooler is a type of cooling device, like an air conditioner, that simply uses evaporation of water. So you basically have pipes that you put air through. This is a simple design. Pipes you put air through, and then you run water on the exterior of those pipes. And the water then evaporates, cooling, drawing heat out of the pipes, drawing heat out of the air inside, and then you pump that air through your house. In what kind of location would that be really effective? There's some locations where swamp coolers are really effective and some where they're very poor. Florida would be poor.
It's in dry places.
In dry places. Places that have names like arid zone. Otherwise known as Arizona. Right? Because it's dry, the humidity is low, you don't have many water molecules that are kind of come in, so basically all the water molecules that leave are gone forever. And so you have a lot of evaporation. Of course, if you go outside and your body is covered with water, what would make you feel colder than just being outside with your body covered with water? Wind. Why would wind make you feel colder?
Yes, sir.
Why do we have wind chill? The water that leaves your body, the evaporation, that gets taken away so it can't come back to you. Because if you didn't have that wind, you would have a higher local humidity just above your skin than you do around you. And so it would slow the rate of cooling. But if you have wind to take it away, then the water that leaves you is gone instead of being right there and able to come back in. This actually plays into, you guys don't even remember Corey Stringer. But Corey Stringer was a football player, offensive lineman for the Minnesota Vikings. And he was, I think he might have also been taking metabolism booster to help him lose some weight. But he was practicing football in reasonably warm weather. In Minnesota, it was reasonably dry at that time of year. But he had on all his football pads and everything. And with all the pads, you don't get effective evaporative cooling because it keeps the moisture in so it can be reabsorbed. So it gets a lot hotter when you're wearing that heavy clothing because the water is in there. His body overheated, organs shut down, and he died from that, yes. There have been a number of athletes who died from overheating during practice, many of them was because they were trying to lose weight by taking metabolism enhancers, things that make your metabolism go really fast, which makes you hotter because you're converting energy into heat. Okay, boiling. Boiling is an interesting process in and of itself. We know that water boils at 100 degrees Celsius, right? Why does it boil at 100 degrees Celsius? Because that's the temperature where the vapor pressure of water is equal to atmospheric pressure. In water, you're going to have tiny little bubbles. And usually, if it's cold water, like 20 degrees Celsius, the vapor pressure, the pressure that you'll have of water molecules in a little bubble, is much lower than atmospheric pressure. And so atmospheric pressure just crushes the bubbles. But as the temperature gets higher, you actually have more water going from liquid into gas phase. Why? Because you have a higher percentage of your molecules with enough energy to break away from the surface. So you get a higher vapor pressure. And so as the temperature rises, the bubbles will grow a little. And when you get to 100 degrees Celsius, the partial pressure of the water is equal to atmospheric pressure. The bubbles now are going to have more pressure inside than atmospheric pressure, which means they grow. And they float up to the top, and that's what we call boiling. So that's why water boils at 100 degrees. It can still evaporate at any temperature, but boiling is where those water bubbles are going to grow. Now, you guys have taken probably chemistry class, and you boiled water in chemistry class. And what did you do? What was absolutely required by any good teacher in chemistry? You what? Okay, yes, it's a safety procedure.
Don't touch hot glass.
Don't touch hot glass. That's a good one. Yes, they always say, this is hot glass, this is cold glass. They look the same. But you always have to throw boiling chips in there. What's the point of a boiling chip?
Boil faster.
It doesn't make it boil
Makes
faster.
it smaller. Or makes it more like less vigorous, like it's less explosive.
Okay, makes it less explosive is an accurate description. It nucleates bubbles. It traps air on the sharp edges. And so you have little bubbles to start with. So as the temperature increases, you have bubbles that then can grow. If you have bubble-free water, you can superheat it. You can heat the water to above boiling temperature because you have no bubbles that are growing. And then all of a sudden, you have a bubble form, and it makes a whole bunch of bubbles form, and the whole thing blows up. Have you guys ever read about people getting scalded by heating up water in a microwave?
Yes.
That's what happens. If you take a nice new mug, an unscratched mug, and you put some nice distilled water, I don't know, obviously they're not putting in distilled water, but you put in some water that doesn't have air bubbles, water that would kill your fish, you put it in the microwave and heat it up, it can get up to, let's say 115 degrees Celsius. And then when you pull it out, you jostle it, you create a little cavitation, about forms, and the whole thing explodes in your face. You get terribly burned. How can you avoid that? Why don't I use boiling chips? They're one of the same questions.
Because your glassware is scratched.
Yeah, my glassware has all kinds of dirty and scrap and all kinds of stuff in there. So I'm nucleating, I have lots of air trapped in there. If you have a scratched up mug, it's going to have trapped some air there and it will start bubbling on where the scratches are and you don't have the problem. So just, don't use new mugs. Use old damaged ones. Okay, let me skip over that one. I talked about water boiling at 100 degrees Celsius. But I said that it boils at 100 degrees Celsius because the partial pressure of water, also known as the vapor pressure, is atmospheric pressure at 100 degrees Celsius. But I've also told you that I have a house in Hartselle, Colorado, where the air pressure is only 70% of what air pressure is here. So air pressure is about 7 times 10 to the 4th pascals. At what temperature will water boil there in Hartselle? You can look at the table and tell me. What's the rule for the temperature when it boils? Water boils at 100 degrees because that's when the vapor pressure is equal to atmospheric pressure. But in Hartzell, the atmospheric pressure is only 7 times 10 to the 4th pascals. So what temperature is it going to boil there? At 90. Our water there boils at 90 degrees instead of 100 degrees.
Is that just because of the elevation?
Well, that worked well. Yes, it's just because of the elevation. Pin there, now it'll work.
Do you mind if I repeat that back to you to make sure?
Absolutely, go for it.
Cool. Okay. So the atmospheric pressure there is lower. So the pressure for the water's vapor pressure to equal atmospheric pressure happens at a lower temperature.
The temperature for that, yes.
Okay.
So that's why at elevation things boil at a lower temperature. Now that makes cooking a little different. Because if I'm going to, let's say, it's a horrible way to cook peas, but let's say I put my peas in water and I boil the water. You know that's horrible because it tastes terrible when you boil your peas, right? How is it going to be different if I'm cooking peas that way in Colorado, where I live, well, where my house is, I don't live there, obviously, compared to here? It's cooking at what? A lower temperature because I'm putting heat into the water. That heat raises the temperature until it starts boiling, and then the rate at which the heat is leaving becomes very rapid when it's boiling, so it just stays there. So I'm cooking at a lower temperature, which means it's going to take longer to cook because of the lower temperature. So we first went there, Amy's trying to figure out how to cook. I'm like, chocolate cooks just the same. Take it out of the wrapper and eat it. Don't even tell her I said that, she'd be offended. Not what I said about her, but what I said about me. So how do we get around that? It's this great invention called the Instant Pot. Or when I was a child, it wasn't just a pressure cooker. What was that? Yeah, it's a pressure cooker that is programmable. As opposed to when I was a kid, the pressure cooker, you just put it on the stove top.
I don't think Brett can
It's
hurt you.
the one that can explode and you have to be.
My mom
Yes.
uses that one.
Yes, back in the day, you would have pressure cookers explode occasionally, and that's very dangerous. So why is the pressure cooker a magical instrument for there? Yeah, it's cooking at 2 atmospheres. You use it up there, it's still going to cook at 2 atmospheres. It cooks the same as it would anywhere else because it's a pressure cooker. What's the purpose of a pressure cooker? It speeds it up because?
More pressure.
More pressure, which means, okay, so let's say you're at 2 atmospheres. What's the boiling temperature of water at 2 atmospheres?
120.
Yes, 120. Roughly 120. So if it's 2 atmospheres, you're cooking at 20 degrees Celsius hotter, which means you can cook quicker. You guys have all heard of Colonel Sanders and Kentucky Fried Chicken, right?
Yeah.
Colonel Sanders was a bona fide Kentucky colonel. What does it mean to be a Kentucky colonel?
No clue.
No. A Kentucky colonel, it's an honorary title. We have honorary titles here in Nebraska. Mike Menard. You guys know Mike Menard?
Yeah, no.
He is an admiral in the Nebraska Navy.
No. What?
That's the equivalent to a Kentucky colonel. Yes.
Nebraska Navy, what does that mean?
Nebraska's own.
Nebraska doesn't have an ocean, exactly. But it's an honorary title given to citizens who have something special.
What does he have?
Is it a joke or is it serious?
It's serious,
It's actually serious.
but it's a joke as well. A serious honor, it's a joke title.
So what does he have?
There was a case a couple years ago where some anti-government protesters were nominated, and the government's like, nominated by a senator, signs off on it, and then finds out who they are and rescinds it, and it causes a big. Okay, that's not the important thing here for physics.
What does that have?
Excuse me?
What is Mike Bobby special?
He sings, makes music albums. That's it. So, yeah. He does children's music. It's special.
Very cool.
So, and because he's a Nebraska admiral of the Nebraska Navy, he can marry people. That's one of the powers given to admirals of the Nebraska Navy. Just like an admiral on a real ship can marry people. Okay, so, or captain on a ship. Colonel Sanders, he invented a recipe of herbs and spices and a method of cooking in a pressure cooker. And he went around selling his recipe and pressure cooker to people. And so if they bought the recipe and pressure cooker, they now had a Kentucky Fried franchise because they could make Kentucky Fried Chicken. What was special was, because of the pressure cooker, they were able to cook the chickens much more rapidly. And that's the birth of Kentucky Fried Chicken. Pressure cooker. This graph has more, though, than just talking about cooking, because if we talk about the relative humidity is the vapor density over the saturation vapor density, or the partial pressure of water divided by the equilibrium vapor pressure of water. Either way you look at it, what that means is it's how much water is in the atmosphere divided by how much it can hold. But the amount of moisture that the water can hold varies with temperature. Notice the axis there, the vertical axis, that's a logarithmic axis. So if you go from, let's say, room temperature here at 20 you can hold about 10 grams per meter cubed. And if you go up to a hot temperature of 40, and of course we can look here and we have the numbers, it was actually 9.4 at, well, that was 17.2 is the saturation vapor density. You go up to 40, it's 44. So if you have the same amount of moisture in the air at 40 degrees, the humidity is going to be less than half as high because the air can hold more than twice as much water. For this reason, weather reports always talk about the relative humidity. It's really not the best thing to measure. What's best to measure is what we call the dew point. The dew point tells you the temperature at which you would have 100% humidity. And so if the dew point goes up, that means you have more moisture in the air. Dew point goes down, you have less moisture in the air. So the dew point you can use to calibrate how much moisture is in the air. Relative humidity does tell you more about how it's going to feel to you. Because if the relative humidity is 100%, you're not going to cool off from evaporation. If the relative humidity is 50%, you'll cool off some. If it's 20%, you'll cool off more. And that's probably why we use it. But that the dew point, that tells you if you get down to this temperature, you're going to have 100% humidity. 100% humidity, the air is holding as much water as it possibly can. What happens if the temperature drops below the dew point? You have more water in the air than it can hold. You're going to have water droplets form, or dew. And of course, if that happens at ground level, we'd say, hey, that's a fog. Because a fog is water droplets in the air. If it's more than 50 meters above ground level, we call it a cloud instead of a fog. Clouds and fog are the same thing. It's just at ground level it's called fog. Above the ground level it's called cloud. And so as you have hot air rise, temperature cools, you have water droplets form, and you have clouds form. Now shifting gears a bit, are you guys familiar with these kind of diagrams? We have two kind of diagrams we're going to show you. This here is a PV diagram, pressure versus volume. And so pressure versus volume, we have a bunch of lines for constant temperature, and it's just assumed constant number of molecules. And so if you have a gas at this temperature, as the volume decreases, as an ideal gas, PV equals nRT. If the volume decreases, and the temperature stays the same, the pressure should rise. So this is following that PV equals nRT curve until you get to this point. When you get to that point, you have a high enough pressure that you start forcing the molecules to condense. And so it goes into water, and then you get here, and then it, actually I said it goes into water. This is undergoing the phase transition into water, and then here's leaving the phase transition. So it's constant temperature during the phase transition. But if you have a high enough temperature, what we call temperature critical, you come through here, and it doesn't really go through a phase transition. And anything that's hotter than that never does have a phase transition. Did you know that? It's possible to go from what is clearly a vapor to what is clearly a liquid without ever undergoing a phase change. Now, changing to a more familiar graph, what you know is a phase diagram, a pressure versus temperature diagram. This is showing the same information fundamentally, just a different set of axes, and now we're saying, okay, if temperature changes and we keep a constant density, here's the critical point. At that critical point, if you have a pressure higher than the pressure at the critical point, there is no distinction between a liquid and a vapor. Or if you have a temperature higher than that critical temperature, which you see for water is 374 degrees Celsius, it's pretty high, you can't differentiate between a liquid and a gas. The thing that's weird about this then is, let's say that we have water, and that water is going to start at the boiling temperature and at 1 atmosphere. And instead of letting it boil, what we're going to do is we're going to simply increase the pressure, keeping the temperature constant. And then we'll increase the temperature, keeping the pressure constant. Then lower the pressure, keeping the temperature constant. Then lower the temperature, leaving the pressure constant. In that process, notice what we did not cut past. We did not pass red. The red line that's separating liquid, L stands for liquid, from vapor, V stands for vapor. So in doing that process, we never crossed the phase transition. But you would clearly say water at 100 degrees Celsius and 1 atmosphere is liquid. And at the end, you're at the same, but you're on the steam side, it's clearly vapor. But never did it undergo a phase transition. What happened was, you had dense water that got less and less dense until at some point you're like, wow, this isn't water at all. This is gas, but it never transitioned. And we see this in astronomy in places that we don't go. Like, for instance, Jupiter. Obviously, no one has been to Jupiter. But in Jupiter, if something goes in, it'll get thicker and thicker and thicker until you're saying, wow, this is totally liquid hydrogen. But never do you have a splash point. Never do you go from gas to liquid. It just got thicker. So that's the critical point. The critical point is the highest temperature and pressure where you can distinguish between the liquid phase and the vapor phase. So it's a specific temperature and pressure for that critical point. Another important thing to note is the triple point. We've talked about this before. The triple point is a very specific pressure and temperature where you have solid, liquid, and gas all coexisting. So there's only one way for a given substance to get to the triple point. Now, you notice the one on the left is for water. The one on the right is carbon dioxide. So the triple point for carbon dioxide is minus 56.6 degrees Celsius and 5.11 atmospheres. We don't normally reach that condition, right? The triple point for water is, 0.01 degrees Celsius. That's something we commonly go across. but 0.006 atmospheres. So we don't commonly get there. You have to pump it down, lower the pressure to get there. There is another very serious difference between carbon dioxide's phase diagram and water's phase diagram. And that is the line that separates the liquid and the solid. Notice in the water diagram, it starts off with a slope that's going back, whereas carbon dioxide is a slope that goes forward. The significance of that comes down to if I have ice, and I have ice at 1 atmosphere. So here's my ice at 1 atmosphere. What's the temperature there? If it's where ice and water coexist at 1 atmosphere? Okay, 0 degrees. So I have ice at 0 degrees Celsius. If I increase the pressure, so if I go straight up on that, what's going to happen? If I go straight up from this point, what phase am I in? I am in the liquid phase. So if you take ice at 1 atmosphere and you put it under more pressure, it's going to melt. Now let's say it was cold ice. Cold ice, so it's ice back here at like, minus 5 degrees. It's still going to be, if you put pressure on it, it melts. This is a very true thing, but it leads to untrue statements. Like when you're ice skating. What's the key to ice skating? Skating. Those skates have a blade on them. And if you look at where the skate has passed, you see a nice shiny sheen in the track. What is that shiny sheen? Water. It's water. It's melted ice. And people will tell you that that's because you have a person's body weight concentrated on a very narrow strip. If you have their weight on a very narrow strip, that tells you the pressure is really high, right? And so it melted because of the pressure. But actual physics experiments say, au contraire. That blade is actually warm enough that it's transferring heat and melting because of the transfer of heat, not because of the pressure.
And that's making it groove.
And so, well, the weight is what's causing the groove, but the melting itself is because of the temperature of the blade.
That's just because it's moving so fast.
Just because of the air around you. I mean, that's what I've read from physics papers. So the thing that says the pressure's melting, it's generally false. But you melting the ice and then you're skating on that water that's very low friction surface. So that's a key to ice skating. If it gets too cold, you can't ice skate anymore because you don't melt the ice. And so your blade sticks.
How cold is it?
I think it's something like minus 30s or somewhere in that ballpark. I don't know offhand.
Kelvin? Celsius?
Celsius, yeah. There's no minus 30s Kelvin. And at that point, it doesn't really matter if we're saying Fahrenheit or Celsius because we're minus 40, and we laugh. Okay, one more thing on this phase diagram. I'm trying to point out things that people generally don't know. The common phases of matter were gas, liquid, and solid. But when I talked about there's more than just the common ones. There's, for instance, the plasma. There's the colloidal suspension. And there are lots of different solid phases. And so Russell looked up for us when we were talking about this before, which phase of water is which. But if you get to a high enough pressure, that water line curves back. So you get to high enough pressure and it's going to come back like this. And so at that point, water behaves like any normal material. But it's a different phase of solid. All right, moving forward. Let's all go to woo clap. Oh boy, no, let's not go to woo clap just because there's only 4 minutes left. Which one of these cannot happen? You cannot go from a solid to a liquid without going through a phase transition. If you look at the diagram, there is no way, this line goes on forever, so there's no way to cross there without crossing the line. So that was the one that was the question. Mechanisms of heating. There are 3 mechanisms for heating. Mechanism number 1 conduction. Conduction is when you have, I'll come back to that, when you have direct contact between two surfaces. So for instance, no, we're not going to do wood clap. You're just indicating, okay.
I'm conducting.
Yes, conducting heat. So if I have like an ice cube, and I directly contact that ice cube, heat will flow. Which direction will heat flow? Okay, from the hotter thing to the colder thing. And so, yeah, it depends on which one's colder. So the safe answer, from the hotter one to the colder one. And the rate of heat transfer, that's energy per time, which we call power, is proportional to the area of contact and divided by the length. So in this case, in the picture, you have a bar with some cross-sectional area that's shown. Notice it's the cross-sectional area. It's the area that would be contacting on either side, divided by the length of the bar. So if the bar is longer, it's going to be slower conducting heat. Shorter, it's faster. That K is a constant that depends on the material. It's called the thermal conductivity. K just stands for constant. We use it everywhere in physics. Like K for Boltzmann's constant. K for constant. And then the change in temperature. The temperature difference from here to here. So in many regards, this is like Newton's law of heating or cooling, right? Newton's law of heating or cooling said that the rate for heat transfer depended on the temperature difference. And that's what you have here for conduction as well. So conduction, direct contact. The next one, just looking at properties of materials. This is in order from highest conduction to lowest conduction, thermal conductivity. So silver is really good at conducting heat. What's really bad at conducting heat? Styrofoam. What is styrofoam? It's what? Kills ears? Okay, kills the ear. But did you guys make styrofoam in like organic chemistry?
I haven't taken it yet.
Styrofoam is polystyrene. It's a polymer that has a bunch of air bubbles in it. And so it's principally air, right? Here's some styrofoam with water in it, apparently. Didn't realize that. It's principally air with some polystyrene that's keeping those air molecules separated. So it's a really good insulator. Right now, all we've talked about is thermal conduction. That air is very poor at thermal conductivity, and so you have very poor conduction through. Polystyrene must also be pretty poor, but you also have to think about that polystyrene. It's very thin channels of polystyrene with air bubbles in between. And so the area is small, which slows down the rate of conduction through the polystyrene. And the length is pretty long, which also slows it down. So styrofoam is a really good insulator, primarily because it's a bunch of trapped air bubbles.
Why is it lower than air?
It's lower than air, I think, because you have polystyrene that's also adding to the insulation. That's what I think. That's all as far as I can go. Down feathers. Down feathers is about the same as air. Why is down feathers just about the same as air? It's trapping air. If you wear like thermal underwear or a knit shirt, the purpose there for warmth is that it's trapping air bubbles. And so heat comes out of your body, it warms up that air, but that air is very poor at transferring the heat. So it basically holds it against your body, and thus you stay warm. Wool, same idea. Glass wool, same idea. So you see things that are largely air, good insulators. Things that are metals are good conductors. How does conduction work? On a microscopic level, it's based on collisions. You have molecules in one substance hitting molecules in another substance, transferring energy. That's the process of conduction. So if you have a longer surface or distance to travel for the heat, you have to have more collisions. That's why it's less efficient. But if you have a bigger area, you can have more collisions per second, more efficient with bigger area. Which material is the best insulator? of this list?
Air.
Air, right, just moving on. And this is a problem I was going to work out. The very quick of it, I asked what's the temperature in the center. Any heat that goes through here has to keep going here. So you say the rate that heat is traveling is the same on both sides. And so you have K copper area over the length, which is distance over 2, times temperature 2 minus temperature center is equal to K for the aluminum times area over distance over 2 times temperature center minus temperature 1. You set those two equal to each other, and then you just solve for the unknown. Okay, convection is the next method of heat. Oh my goodness, look at the time. Convection is actually traveling of a material to take the heat. So if you have a convection oven, you heat up air and you blow that hot air onto your food, and that hot air is bringing the heat. I just have to talk about the last one. I'm going to stop. The last one is radiation. There's no equation for convection. Radiation is actually waves that are carrying the heat. And the radiation equation is a little more complicated. The rate of heating for radiation is sigma. That's the Stefan Boltzmann constant. I gave you its value down here. It's a constant. Epsilon is a number that tells you, it's called the emissivity, tells you how efficient something is at absorbing or emitting radiation. It's the same efficiency for both, times the surface area that's absorbing or emitting, times temperature to the 4th power. What units should you use for temperature? Kelvins, because it's not a change. And then I had a problem I was going to do, but we have to stop. Have a happy Sabbath. Enjoy Jose Rojas, whom I have known since I was like 6.
Oh, yeah, no.